Hi, I'm Nathan.
And I'm Isaac, and this is our demonstration video for MAE 535.
Today we're demonstrating the Hall effect sensor.
The Hall voltage is the result of the Lorentz force acting on electrons as they pass through a conductor in the presence of a magnetic field. The electrons are pushed towards one side of a plate according to the right-hand rule, and the buildup of electrons on one side causes a buildup of negative charge, which causes a buildup of positive charge on the opposite side. This resulting differential voltage can be measured as the Hall voltage. As the derivation on the right shows, that the magnitude of that Hall voltage is the current times the magnetic flux divided by the electron charge density, which is a material dependent property, divided by the thickness. Our sensors were constructed using adhesive and metallic film and 4 wires. The wires were adhered to the film using adhesive tape, and then masking tape was used to structurally support those connections.
To construct our sensor, we looked at a couple different materials that we had readily available to us. We had some copper tape, we had a graphite tape, and then household aluminum foil. We built the sensor by putting 2 layers of the tape and then a couple wires. We had the wires in the short direction measuring the Hall voltage, and the wires in the long direction measuring or supplying the input current flowing through the system. At a hint from Dr. Buckner, we looked for materials with good free electron properties. The graphite was at the top of the list, but it had a very high resistance, so it didn't flow as much current, which we need for a Hall voltage. The other 2 metals could flow the current, but they didn't have the right charge or free electron properties, so they didn't really work in our studies. In addition to homogeneous materials, we tried a laminate of copper and graphite to see if we could blend the properties of the 2 and make a sensor that would work a little bit better for us.
The circuit begins at the DC power supply, which feeds voltage into a current management resistor bank, which steps the current down to roughly half an amp, as can be indicated by the power supply. That current is fed through a Hall effect sensor, which is then fed off to ground. The voltages in the transverse direction of that sensor are then fed into an op-amp, which is set in differential non-inverting configuration, where the resistors are selected for roughly a gain of 1,000. The op-amp of that, or the output of that op-amp, is then fed into the digital multimeter, which reads the amplified Hall effect voltage. As you can see now, we're measuring the Hall effect voltage of a sensor with no magnetic field. We recognize this should be roughly 0, theoretically, but stray voltages and noise in the system cause some slight DC offset. So our experimental plan was to take a baseline measurement with no magnetic field and then subtract that result from identical measurements in the presence of a magnetic field. With some effort, we carefully added these very strong neodymium iron boron, very strong magnets to the Hall effect sensor to apply maximum magnetic flux through the sensor with minimal fringing effects. And so this maximizes the Hall effect voltage from the sensor. And you can see, applying the current, that this results in a different amplified Hall effect voltage than the baseline value. You'll also see that the voltages are varying a small amount due to noise in the signal. To compensate for this, we took averages of both the baseline and the magnetic field configurations and averaged these results to reduce the signal to noise ratio.
So in conclusion, we have the data that we collected from those previous 2 video segments. You see the baseline was about 0.83 volts without the magnets and 0.75 with the magnets. So taking the difference of those 2 and dividing by the gain results in a Hall voltage of about 87 microvolts, which was within the range we predicted in our order of magnitude studies. So positive results overall. Some takeaways were the small nature of the Hall voltage being easily lost in sensor noise, as well as material properties both from the conductor and the availability of rare earth magnets. So I hope you enjoyed the video. Thanks for watching.